Good morning. I'm Gokul Swami, and I'm a senior machine learning scientist with Amazon. I take this opportunity to welcome you to this session on Introduction to Probabilistic Graphical Models. This will be a two-part session, with the first part covering the basics and a second part involving more advanced concepts. Moving on, we will start off with a basic introduction to probabilistic graphical models along with some real-world applications. We will then move on to discuss directed graphical models and Bayesian networks. Following this, we will touch upon undirected graphical models, factor graph, and also discuss this in the context of Markov networks. Subsequently, we will discuss how to do parameter estimation in graphical models and also discuss the inferencing problem. We will close out the first part with a discussion on why inferencing is hard, and in part two, we will continue the discussion on what methodologies can be employed to make inferencing practical for real-world problems. So an example of a graph network is shown in this slide. So A, B, and C are three nodes, and the red arrows are the edges that link the vertices. The nodes ideally represent random variables, and the edges encode the relationship between these random variables. Also, as you can infer from the graph, the arrows are directed from one vertex to another. So this essentially encodes the directional or causal relationship between the node entities. As an example, consider a graph which comprises of nodes which are essentially diseases and symptoms. So you would expect the arrows to flow from the disease towards the symptoms, because ideally a disease can cause symptoms but not the other way around. So such graphs are often referred to as directed graphs. In certain instances, no such causal relationship might exist, and in such cases, the graph is said to be undirected. As an example, consider a graph comprising of people shaking hands at a party, wherein the nodes are the people and an edge represents if any two people shook hands. In this case, the graph is undirected, as no directional relationship can be established. I mean, shaking hands is kind of a very mutual thing, and there's no directionality associated with it. So in the next few slides, we will see several examples of graph networks in real-world scenarios. Before I proceed further, I would like to, kind of state that it is assumed that the audience is familiar with basic concepts in probability to be able to grasp the contents of this lecture. Okay. The first application we pick up is spam filtering. Right. So in this graph, spam is a random variable that takes on two values, 0 or 1. W1, W2 up to Wn are words that are drawn from, let's say, a finite dictionary and are essentially dependent on what is the value of spam, the spam feature. So we use the word dependent a little informally here, but to make it more formal, we can view the graph as a generative model where the value of spam dictates what kind of words W1 to Wn are likely to be. So let's say spam is equal to 1. Then the conditional probability of words such as lottery, offer, exclusive, which we quite often associate with spam, would have a fairly high probability of occurrence. So another interesting aspect of the graphical model is that given the spam nodes, the words W1 to Wn are independent of each other. And this is often referred to as conditional independence. So conditional independence is a fairly important concept that will be occurring several times in this lecture. So conditional independence allows us to factorize the probability distribution as shown in the expression below. So this expression here. In a real-world scenario, the words W1 to Wn in a sentence, right? If you look at, let's say, an email sentence, are unlikely to be independent of each other because there is a certain structure associated with the language. But in many cases, in real world, even for real world problems, you make simplifying assumptions like the one we have made here, saying that given spam, the words are independent, to be able to arrive at a feasible probability distribution that can be computed. Right? So, and we do this often to make machine learning and inferencing easier. So moving on, Now we kind of give out more examples of what kind of real world graphical models do exist. So here is one such example. So we look at a graph of diseases versus symptoms. So as expected, the graph is directed with edges originating from the disease node and going to the symptom node. The symptom node is the one at the bottom here, right? Indicating what symptoms are caused by any given disease. So using this graph, as a learned graph, and given a list of symptoms, we would then be able to infer what is the most likely disease that is causing all the symptoms. So this is one example of how graphical models can be employed in practice. So another example is from natural language processing, where we use a hidden Markov model to assign parts of speech tags such as noun, pronoun, etc. to the words in a sentence. So this can be very useful for a host of applications such as information retrieval, text to speech, etc. So in fact, Amazon Alexa is one very good example where you can use a network of this type to do text to speech synthesis. Graphical models are also very useful in vision tasks, wherein, for example, in the picture on the left, we can think of each pixel as an observed node represented by blue circles. The observed nodes are in turn connected to hidden nodes represented by red circles, which encode more semantically useful information, such as whether the given pixel corresponds to the, let's say, animal class or sky, grass, etc. So once again, given the hidden node, the observed pixels are independent of each other. The hidden nodes, in turn, are connected to their immediate neighbors, representing the fact that neighboring pixels have a very high likelihood of belonging to the same class unless there is a strong evidence to the contrary. A graph of this nature can be used, for example, to perform image segmentation with a certain number of classes. So with this last example, we will move on to discuss the mathematical underpinnings of directed acyclic graphical models, or DAGs, which are also often referred to as Bayesian networks. So to understand directed graphical models in a little more detail, we will make use of the canonical student network example that is shown on this slide. So this network has 5 different nodes: difficulty, intelligence, grade, letter, and SAT. So difficulty signifies how difficult a given test was, with 0.6 indicating that the test was not difficult and 0.4 indicating the test was difficult. Right? Intelligence signifies how intelligent the student is, with a 0.7 probability the student is not intelligent and a 0.3 probability the student is intelligent. Grade essentially has 3 levels: 1, 2, and 3, with 1 indicating a good grade, 2 indicating a medium grade, and 3 indicating a poor grade. Grade here essentially depends on the difficulty of the exam and also how intelligent the student was. Then there is letter, which depends on grade. So letter here signifies, let's say, a letter of recommendation, and it obviously must depend on grade, because if you get a good grade, then it is very likely that your professor will write you a good letter of recommendation. Finally, SAT is, let's say, a score on an external test like JEE, for instance, and has 2 levels, S0 and S1, with S0 indicating a poor SAT score and S1 indicating a good SAT score. Now, SAT here essentially depends only on intelligence of the student, as to how intelligent the student is. Okay. So the table next to these nodes kind of encode the probability or the conditional probability distributions of those node features, right? So here, if you look at difficulty, you have 2 levels of difficulty, D0 and D1, and the numbers there, 0.6 and 0.4, correspond to the probabilities associated with those difficulty levels. Since difficulty does not really depend on any other node, right? It's an independent random variable in that sense. And so therefore, there is no conditional aspect to difficulty. The same applies for intelligence. So intelligence, essentially, there is no other variable or node which influences intelligence, and therefore there is no conditional aspect to intelligence as well. So moving on, now if you look at the SAT variable, right, or SAT node, things become a little more interesting. SAT now depends on the intelligence of the student. Intuitively, you would expect if a student is intelligent, then his SAT score would be high. Whereas if a student is not intelligent, then his SAT score would be on the lower side, right? So now, since SAT essentially depends on intelligence, we will now, to enumerate the probability distribution of SAT, we will have to enumerate it for all possible values of intelligence. So that is what is shown in this particular table here, wherein you have the probability distribution conditioned over two different values of intelligence, with I0 being intelligence of zero, that is low intelligence, and I1 being high intelligence. So in the case of low intelligence, you can see that the intersection of I0 and S0, the probability value there is 0.95. So what this essentially signifies is that if the student is not very intelligent, then what is the probability that his SAT score would be low? And that is fairly high, which is equal to 0.95. And again, this is kind of makes sense because like we discussed earlier, a student with a lower intelligence is likely to do poorly on this particular test. On the contrary, if you look at the case where let's say the student is intelligent, but his SAT score is still poor, which is S0, intersection of I1 and S0, you can again find the probability value there to be 0.2. So here again, this makes a lot of intuitive sense because if the student is intelligent, then there should be a lower probability of him doing poorly on this test, right? So this is how you would essentially encode the conditional distribution of SAT given the intelligence feature, right, or given the intelligence node. And this is a very, very important aspect in Bayesian networks. So finally, we look at the node associated with the grade, right? Like I had mentioned earlier, the grade has three different levels, 1, 2, and 3, with the 1 signifying a good grade, 2 signifying a medium grade, and 3 signifying a poor grade. Interestingly, grade depends on both the difficulty as well as the intelligence, right? So now when you start enumerating the conditional distribution of grade, you will have to account for all possible combinations of difficulty and intelligence. Now, difficulty takes on two possible values, intelligence takes on two possible values. So therefore, the total number of enumerations in this particular case happens to be 4. And that is I0 D0, I0 D1, I1 D0, and I1 D1. Right? And that is essentially what is shown in the table next to the grade node. So, so again, to take an intuitive example, the question, let's say, if you can read off this table, what you would likely to be infer is that what is the probability of the grade being poor, which is G1, given that the student is not intelligent as well as the test is not difficult. In this case, it happens to be zero point 0.3, right? So in a similar fashion, you can kind of take another example wherein you can ask the question: what is the probability that the student gets a poor grade when the test is difficult, as well as the student is not intelligent? So if you look at this table, you will find the corresponding value to be 0.05. And this makes a lot of sense because if the test is difficult as well as student is not intelligent, then you would expect this value to be fairly small. Now the question is, how did you even get these numbers? How did you fill up this table? Right? These numbers don't appear magically. They are learned as part of the parameter estimation process that we will discuss in the later portions of this particular lecture. But what this graph does do is to lend a particular structure to the probability distribution or the joint distribution of all these features, as we will see in the next slide. So we are ultimately interested in characterizing the joint distribution because, as we will see later, having the joint distribution lets us characterize any marginal or conditional distribution that we may be interested in. So typically, let's say if we had some kind of a magic wand that gave us the joint distribution, then we would be sorted for, in all practical purposes. But for most cases, it is next to impossible to characterize a joint distribution without assuming some kind of relational structure. So the Bayesian network we have been discussing so far helps us break down the joint distribution into manageable chunks, if you will, and this makes it much more simpler to learn the network parameters. So the one way we would essentially construct a joint distribution, but before I go into that, just a note on what a joint distribution essentially implies is essentially the probability of co-occurrence of all the features. That is probability of D, I, G, S, L. That essentially is what constitutes a joint distribution in probabilistic parlance. Now, given this graph structure, how would you break down this joint distribution? So let's start with the letter, right? Letter node. We can see that the letter node depends on the grade. So we write down the first expression or the conditional expression, which is the joint distribution equals to the probability of letter given grade, right? And that's the first term that you see on the right on the equation that is shown in white on this particular slide. So now that we are done with letter, let's move on to the node grade, right? Now, as we can see, the grade essentially depends on the difficulty and the intelligence. Right. So then how would we, the way we would write down the conditional distribution in this particular case would be probability of grade given difficulty, intelligence. And that is what is shown as the second term on the right of that particular equation. And then moving further up, let's say we hit the difficulty node. We can see that nothing really influences difficulty. While difficulty influences the grade really does not influence difficulty. So the difficulty in some sense is an independent node or independent feature. So we just take the probability of difficulty and multiply it with the expression that we have gotten so far. And then the same story applies for intelligence. So you end up with multiplying probability of I to whatever the product you had up till now, right? And then finally, let's look at the SAT node. Clearly, the SAT only depends on the intelligence, right? So if you were to write down the conditional expression for this particular case, you would write probability of S given I, where I is the intelligence. So this is how you would essentially break down, let's say, what would have been a complex probability distribution into a much simpler expression based on conditional distributions that arise out of this particular graph structure. So I hope the way we have broken down this joint distribution is clear, because that essentially forms the crux of the Bayesian network, and it makes both parameter estimation as well as inferencing a much simpler task than it would have been otherwise. Okay. So far we have discussed the directedness property of Bayesian networks, but there's one particular aspect that we haven't really paid much attention to, is essentially what is known as acyclic or the acyclicity. So I think I kind of previously mentioned that Bayesian network essentially is a directed acyclic graph. So we already know what directed is, but let's pay a little more attention to what is probably meant by acyclic, or what the acyclic property is. Take a look at this graph on this particular page, right? And it has three nodes, A, B, and C, and there are arrows or edges that emanate from this node and are directional and end on some target node, right? There's a node that goes from A to B, and B to C, and C to A. Now, a graph is said to be cyclic if you can start at a particular node, follow the directional edges, and arrive back at the same node, right? In this case, there is such a path from A to B, B to C, and then from C to A. So this graph essentially has a cycle in it, or it's a cyclic graph, right? Now, why can't we have cycles in our graph? What essentially is the problem there? So now let's look at a simple characterization of the nodes or the probability distribution at the nodes. So now you can see that the node A depends on the node C. So therefore, if you were to write down the conditional distribution of A, you would enumerate it based on the different possibilities of C, which being C0 and C1. And so we have taken a particular example where A0, or a value, probability of A taking on a value of 0, when C is 0 is equal to 1, and the probability of A taking on a value of 1 when C is 0 is equal to 0. And in a similar fashion, if you look at the node B, based on the direction of the arrow, you can infer that the node B depends on the value or the feature corresponding to the node A. So once again, you can kind of enumerate the probability conditional distribution of B given the two possible choices of A. And in a similar vein, you can do it for the node C as well. Now, if you were to essentially estimate the joint distribution based on this network and estimate the joint distribution for, let's say, a particular case where A equal to 0, B equal to 0, and C equal to 0, you would essentially end up with an expression like this, right? So you would split the joint distribution as probability of A equal to 0 given C equal to 0 times probability of B equal to 0 given A equal to 0 and probability of C equal to 0 given B equal to 0. Right? This is something that we have learned as the process that we followed for the student network example as well. So if you actually plug in the values, you will find that this probability actually tends to be equal to 1. Now, let's look at another example where A equal to 1, B equal to 1, and C equal to 1, and we are interested in characterizing the joint distribution of this particular feature set. So once again, if you expand it, you will find you follow a similar process wherein you have probability of A equal to 1 given C equal to 1 times probability of B equal to 1 given A equal to 1, because the node B only depends on the value of node A, and then probability of C equal to 1 given B equal to 1. And if you plug in the values, you once again find that this probability happens to be 1. Now, this is a major contradiction, right? Because you cannot have two different probability values being equal to 1. It kind of violates the basic concept that the probabilities have to sum to 1. And this is one of the reasons why having cycles in your graph essentially makes it fairly difficult or even impossible to properly assign properly get a proper representation of conditional distributions. So Bayesian networks essentially must be acyclic in order to guarantee that their underlying joint distribution sums to 1 and it is properly normalized. Okay, so I'm going to take a brief diversion here. So while we mostly remain focused on directed graphical models and Bayesian networks, I'm going to touch upon undirected graphs in this particular slide. So as mentioned earlier, undirected graphs result from situations where a clear causal relationship cannot be established between the nodes. For example, in the image on the left is tiled into m cross n nodes, with each node connected to 4 of its neighbors with no directionality inherent. Here, instead of dealing with conditional distributions, we will make use of potential functions, the chi of C, which are defined over a clique. So clique is nothing but a set of nodes that are connected to each other. So in this particular example, a clique is formed by any set of two nodes which are adjacent to each other. Right? The joint distribution then effectively factorizes over all possible maximal cliques, as shown in the equation on the slide, with Z indicating a normalizing factor to ensure the distribution sums to 1. The potential functions are something we define, such as let's say the exponential functions or any other function suitable for our particular purpose. The graphs resulting from such a presentation are also often referred to as factor graphs, because the terms in the product essentially are some kind of factors, which essentially get multiplied to construct the joint distribution. So there are many examples of undirected graphical models, such as conditional random fields, which I am guessing that you would have probably learned about in another lecture. But however, for this particular lecture, we will mostly remain focused on directed models and not discuss too much of undirected graphs. So I encourage you to kind of go back and study, and go dig deeper into undirected graphs and see how they are very closely related to what we are studying in terms of directional graphs and Bayesian networks. Okay. So we did post this question earlier in terms of how did we essentially get those values in that student network? How do we know what those probability values are? right? So typically there are multiple scenarios. One is, let's say you have an expert on your side who sits and fills out that table for you, right? He has a lot of domain knowledge. He understands the problem in and out, and is sitting there and filling out all those values for you, which essentially make a lot of intuitive sense, like we did for the student example. Um, but for a large majority of problems, you would really not have an expert who can do that for you, or the problem scale itself would be so large that it becomes infeasible for an expert to really, start filling out the probability tables, given the number of enumerations that would result from a large graph. Right. So how exactly then can you go about in a principled way to establish to estimate those parameters? So let's motivate this with a simple example of, let's say, a graph with a single node and no edges. So since this graph, this is also a very simplistic example of a Bayesian network. So here, let the probability of, so this graph, this node, particular node, let's say is the coin toss, right? Where the probability of heads is represented by a theta, and the probability of tails is 1 minus theta. Right. So now, how would you really estimate this particular theta? Theta is the parameter here of interest that we are yet unaware of, and you would like to estimate. So this is fairly straightforward. You would toss the coin n times, okay, and then in those n trials, you would perhaps notice that there are n h times heads occurring and nt times tails occurring. So then what you would do is you would essentially construct a likelihood in this particular form, theta times theta to the power nh into 1 minus theta to the power n of t, nt, sorry. And then take the log of this to arrive at an expression of this form. And then if you actually differentiate this with respect to theta and set it to 0, you would end up with this particular expression, right? Which is very intuitive. I mean, the probability of heads is the number of heads given by the total number of trials. So this is essentially a maximum likelihood estimate. Let's say if this particular equation, the log likelihood, was very complex, in which case it doesn't really allow you to, compute a gradient and set it to 0 and solve for it analytically, then you would end up using the workhorse of machine learning, which is the gradient descent, to solve for this particular parameter estimate. So both of these methods, the analytical solution as well as the gradient descent procedure, would help you converge towards the optimal theta, which in this case is referred to as the maximum likelihood estimate. So while we have done this for a very, very simple graph, which is a single node coin toss example, you can extend it to any kind of network. So the same concepts would apply to the student network as well, wherein all those values that we saw on this probability table there would then become parameters, and then based on the number of training samples that you see. For example, one training sample, you would have a particular difficulty, grade, letter, SAT, and intelligence, and for some other sample, those values would be different. You take all these training samples, form the likelihood expression, and then apply gradient descent to find to fill those values in those probability table, or find the values of those parameters in those probability tables. So in that sense, nothing changes from this very simple example to the student network, and the same can also be extended to even more complex networks, because it's a very well established and a straightforward method to do parameter estimation. Okay. Uh, so given a parameter set, right? Like I said, let's say you have a training example wherein you have the grade, letter, intelligence, SAT, and so on. You would be able to, construct a likelihood for that particular training example, right? Given the set of parameters. But then, what happens if, let's say, one of those parameters, one of those features are missing? For example, let's say a teacher was making recorded all these values for a particular student, but for some reason forgot to include the grade in the recording. So in this case, the grade becomes a missing feature. So such cases are far too common in real world examples, and therefore we need to deliberate on an approach to solve for it. So one very potent algorithm that can handle such cases is the expectation maximization algorithm.
So here we assume that the missing features are characterized by a latent vector z, uh, and then we first compute the probability of z given the x and the current estimate of theta. Theta is our entire parameter set. So once we have this distribution, we compute a weighted likelihood or the expectation of probability of x comma z given theta dash under the distribution of z given x comma theta, and then re-estimate theta dash that maximizes this particular likelihood. Right. So this process is continued in an iterative fashion until convergence. So to get an intuitive understanding of what is happening, let's take a simple example of, let's say, given x and the current estimate of theta, uh, you are somehow able to estimate z or the missing features very, very accurately, right? In that case, the probability of z given x comma theta would tend towards a delta function because you know exactly what the value of z is going to be. Because given the x and theta, you have very, very good knowledge of what those missing features values are. Then what you do is, in that case, if you look at the m step, so what happens to the expectation there, right? So if you take the expectation of z given x comma theta, since p of z given x comma theta is a delta function, so the expectation essentially vanishes, and you only are. So what essentially then happens is that you substitute the value of the very confident estimate of z that you have back into this expression for likelihood. You fill in the missing features, and then kind of use gradient descent on that particular likelihood to estimate a better theta or theta dash. Right. So in a general scenario, what would really happen is that you would not be able to very, very accurately identify what those missing feature values are likely to be. In that case, you will end up with, let's say, a probability distribution of z given x and the current estimate of theta, and then what you're essentially doing is that you're plugging those values of z back into your likelihood expression, but also weighting it by the probability of that z occurring given the observed features x and the current estimate of theta, right? And then you do this in an iterative fashion. For example, you get a better theta dash, and then you go and get a better estimate of z, and then you come back and get a better estimate of theta dash, and then you do this in an iterative fashion until you get a good you get a good solution wherein the parameters have converged and you are able to address this missing features problem very effectively. So this is a very, very simplistic, over-the-top explanation of what expectation maximization is trying to do. So we have, of course, glossed over many of the mathematical underpinnings of EM, and to be honest, an entire lecture can be devoted on this topic. But I don't think we will have the time to go into those kind of details in this particular lecture. Okay. So we discussed maximum likelihood estimation. But then, is maximum likelihood estimation suitable for all practical purposes or all problems? The answer apparently is a no. So let's take a simple example. Once again, we go back to the coin toss problem. So let's say somebody wants to estimate the probability of heads. So this person went and tossed the coin twice, and in both cases, it resulted in a heads. Now, if we use the Emily estimate for P, which was the number of heads divided by number of trials, you will get 2 divided by 2, which is equal to 1. Right? So then the person will conclude that the probability of tails occurring is 0. Is this so? This of course is grossly incorrect, right? So even a lay person would be able to tell you that, hey, you haven't really conducted sufficient trials for you to be able to get the accurate probability in this particular instance. So if you take a counter, if you, let's say, observe 400 heads and 600 tosses, then you're way more confident of your estimate of probability of heads compared to let's say conducting just 2 trials. So what is the what really is the problem here? The problem is that the maximum likelihood estimation does not incorporate any notion of confidence in our estimates, and that can prove problematic, especially in scenarios where your data set is limited
And let's say even in scenarios where you're learning a large set of parameters, but you really don't have sufficient data to be able to characterize them very effectively. So then, what is the workaround for this? So what we need to do then is to move away from this maximum likelihood estimation concept and start looking at the problem from a Bayesian statistical viewpoint. Okay, so so what exactly is Bayesian modeling? So sorry. So when we are doing likelihood estimation, what we essentially end up doing is we take the data and we take the probability of the data under given, let's say, probability of x given theta, or the probability of data under the parameter set that we're trying to estimate, and then try to maximize it to get the most optimal value of theta. That is your bare basics likelihood estimation. But in general, if you look at that is from a Bayesian perspective, why should theta be a point estimate? Theta itself can be a distribution, right? So let's say if you look at the distribution of theta given the data that you have collected, that is p of theta given x, you can split it using the Bayes theorem in this particular fashion, where probability of theta given x is equal to probability of x given theta into p theta divided by p of x. So now you can see that basis this particular expression, p of theta given x is no longer a point estimate, but it's a distribution, right? And this, so what is the benefit of doing this is that if you're able to estimate a distribution for theta, you are able to get a very accurate sense of how confident you are in your estimate of theta, and that is what is very important in terms of constructing this Bayesian model. Well, one problem with estimating this distribution is that you have a p of x appearing in the denominator there, which is the probability of the joint distribution of the data, right? But that is not easy to estimate. In most real-world examples, it will be practically impossible to estimate this particular distribution, which is p of x. Right? So then what we can do is, since p of x does not explicitly depend on theta, we can remove it from the expression and put a proportionality constant there. That p of theta given x is proportional to p of x given theta into p of theta. Now it's interesting to see the two terms on the right here. The first term, as we talked about earlier, the probability of the data given the current given the estimate of the parameters theta is nothing but the likelihood, right? And in MLE, what you would essentially do is go ahead and maximize its likelihood to find the best possible theta. But then you also have another term sticking to the right, which is p of theta, right? So this term is the prior, wherein you encode some prior knowledge about your about your estimate of theta. Right, this prior knowledge could be as simple as saying that, hey, I believe theta to be a uniform distribution, or it could be a Gaussian distribution, or a beta distribution, or whatever it is. You have some idea of what theta should look like, and then you can encode that into your prior. And then what you do is you can go ahead and maximize this particular expression, that is p of theta given x, which is called the posterior, and arrive at an estimate which is known as the maximum a posteriori estimate, or commonly known as mapped estimate. Okay. So let's take an example once again. How would you do this for a simple coin toss problem? Right. Once again, p, let's say, is a probability of heads, right? Where and xi is a random variable that you observe. Let's say you do n trials, x1 to xn, where xi equal to 1 if the ith trial resulted in a head, and xi is equal to 0 if the ith trial resulted in a tail. So then how would you essentially construct the likelihood for this function? Likelihood for this would be likelihood given theta, that is p of x given theta, in this case would be this particular expression here, right? So p of xi times 1 minus p into 1 minus xi. So when xi equal to 1, or you observe a heads, then the likelihood for that particular training example is p. Whereas if you observe a tail, which is xi equal to 0, then the likelihood happens to be 1 minus p, right? Which is very, very, very straightforward. Now, apart from this, we also do one more thing. We assume a prior on p. So now p is no longer a number, but let's say we characterize p by a distribution, right? And in this case, p happens to be a joint beta distribution, right? So we have assumed p to be take the particular form of a beta distribution characterized by the two parameters A and B. So why a beta distribution? So that's again is a fairly interesting question, and one that we will try to answer in the next slide. So typically, the prior is chosen such that it satisfies
what is known as the conjugacy property. So by choosing a conjugate prior, right, we ensure the posterior distribution. Remember, we had discussed the posterior distribution earlier, which is the likelihood times the prior. So if you choose a conjugate prior, where p theta becomes a conjugate prior, then what happens is the posterior distribution ends up having the same form as the prior distribution. So this has huge ramifications when performing variational inferencing, as we will see in the second part of this particular lecture. So for the coin toss problem, once again, we assume P to follow a beta distribution, which is characterized, basis this expression here. And then recall that we have the likelihood, which is given by this particular expression for the, let's say, likelihood for the ith trial. So then to compute the posterior, which is probability of theta given x in this case, the posterior for the ith example would be probability of p. The theta parameter here is p, the probability of heads given x of I, right? Which is then proportional to the prior term, which is probability of p, which is nothing but your beta distribution times the likelihood, which is the probability of xi given p, the expression for which we had derived in the last slide. So if you do this, if you compute this particular expression, you end up with an expression of this particular form. Right? So interestingly, if you look at this particular expression here that we arrived, so now if you actually conduct n samples, right, n trials, then your complete posterior on the entire data, right, it takes this particular form. You assume the trials are independent, so the probabilities, the likelihoods multiply, and therefore you end up with an expression of this particular form. And if you actually end up looking at this expression, you will notice that this expression is nothing but the beta distribution characterized by these parameters. So now it kind of jumps out at you that by using a beta prior, your posterior also ends up being a beta distribution. Right, so that is essentially the beauty of using a conjugate prior, and it, like I said earlier, it has a huge importance in terms of variational inferencing and so on. Right now, as I had talked about earlier, there was a concept of maximum a posteriori probability, or MAP. The way we would do that is by maximizing the posterior in terms of the parameter theta, in this case p. If you did that, you would end up with an expression of this form: n plus a divided by capital N plus a plus b, where a and b, remember, are the parameters of the prior beta distribution, and n is the number of heads, and n is the total number of trials. Interestingly, now look at this case where, let's say, small n equal to 2 and big N equal to 2, right? So in this case, they don't really have an outsized influence on your probability estimates, because they are kind of regularized by the a and b parameters that appear in the expression. Whereas, let's say, both small n and big N are, let's say, big N is large. Let's say you conduct like 10,000 trials. Then the parameters a and b that are appearing in the numerator and denominator pretty much lose their significance, right? I mean, the ratio is entirely determined by the value of small n and big N. So this kind of encodes, this estimate kind of encodes the confidence in the sense that when you have a large number of trials, it tends to pivot more towards, what the probabilities that you observe basis the empirical estimates arising from the trials. Whereas if the number of trials is very small, then it gives sufficient importance to the prior distribution so that you don't go making absurd conclusions basis the data. Okay. So the idea behind training a Bayesian network is to be able to ask questions of this network and arrive at suitable answers that could either be point estimates or probability distributions. Essentially, there are three main types of inference. Marginal inference involves finding the probability distribution of a given node in a trained network.
posterior inference, we talked about the posterior distribution earlier. Posterior inference involves finding the probability distribution of a set of unobserved nodes given some other nodes which have been observed. And finally, the map estimates, map inference, wherein you want a point estimate of the unobserved features by maximizing the posterior probability. So we will look at these three inferences by taking the example of the student network. So as I was mentioning in the last slide, you have the three different forms of inference: the marginal, posterior, and map inference. So if you look at the marginal inference, one particular example in case of student network would be, let's say, finding the probability of L, where L is a letter and it can take on two values, 0 or 1. So the way we would estimate this marginal distribution is through a process called as marginalization, wherein you take the joint distribution and integrate out all the variables that you're not interested in. So, for example, to find the probability of L, you would take the joint distribution and integrate out the difficulty, intelligence, grade, and SAT scores. Right. So this summation itself can be made a lot more efficient by exploiting the graph structure and the particular form of the joint distribution, which allows us to move certain terms, in and out of the summations to make the process more computationally efficient. To give the example of posterior inference, so one particular example could be, for example, what is the probability of the letter given the SAT score is good, right? So in this case, again, you could use the joint distribution and arrive at an expression like this to be able to estimate this posterior distribution. And finally, an example of a maximum a posteriori inference, for example, could be where somebody asks you a question that you already trained this graph. Can you tell me what is the what values of the SAT score and the letter will maximize my joint distribution such that the difficulty is 1, intelligence is 0, and the grade is kind of good, right? So these kind of questions can be very effectively answered using the graph architecture and the joint distribution that we have just learned using the parameter estimation techniques that we described earlier. So in the last slide, we kind of looked at marginalization as a means to performing inference in Bayesian networks. But then that is not a process that is suitable for all practical purposes, right? Especially in the case of large graphs, marginalization becomes computationally inefficient, and in several cases it may not even be possible to use this particular approach to perform inferencing. So let's take an example. Let's say you have a graph with 6 nodes and you are interested in finding the posterior, that is probability of x1 given y1, y2, y3. So then the way you would do this is to marginalize out the features x2 and x3. So let's say the cardinality of the feature is represented by mod of x. So in this case, for let's say estimating the posterior for a given value of x1, you would have to perform mod of x2 into mod of x3 summations, right? And then doing this for all possible values of x1, you would end up with mod of x1 into mod of x2 into mod of x3 summations. So let's say in general, the cardinality of the feature space is S and the number of features is N. Then you end up performing close to S of the order of S to the power N computations or summations to be able to arrive at this posterior distribution. So this is kind of apparent that for large N, a large number of features and a higher cardinality, this computation becomes extremely inefficient. And for all practical purposes, for real world graphs, this is not an approach that is feasible. So to overcome this, we can use a technique called belief propagation, which is an iterative process in which neighboring variables, for example, x3 and x2, talk to each other, passing messages such as I, variable x3, think that you, variable x2, belong in these states with various likelihoods. So after enough iteration, this series of conversations, between the nodes is likely to arrive at a consensus that determines the marginal probabilities of all the variables. So in the case of graphs which don't have any cycles or loops, so these marginal probabilities or the beliefs are actually exact. That is, they converge exactly to the marginal probabilities of the nodes. So but not going into the mathematical details here, but the process kind of mirrors a dynamic programming slash Viterbi coding approach for graphs which have no loops, which makes the process a hell of a lot more computationally efficient than what you would have with marginalization. Okay, so then what is the problem? So we already discussed marginalization and said that that is extremely computationally inefficient, and therefore we kind of went towards belief propagation. But then it's been noticed that for large dense graphs, as for example, let's say a graph that would involve social networks or Twitters or something like that. In those cases, also the belief propagation tends to become computationally inefficient. So that's where we come across the need for having a different approach towards performing inferencing on Bayesian networks, and two possible solutions emerge in terms of Monte Carlo methods such as Markov chain Monte Carlo sampling, and the second approach being variational inferencing. And both of these will be discussed in greater detail in part 2 of this presentation. All right, so with that, this brings me to the end of the part 1 of this lecture. I hope you are able to grasp the basics of probabilistic graphical models and have a good understanding of what graphical probabilistic models are, the way we perform parameter estimation on these models, and a couple of approaches for performing inferencing, and also what really constitutes inferencing in these models. So thanks a lot for your attention. I would be happy to answer any questions at the end of this lecture, but do stay tuned for part 2 of this series. Thank you.